Did you know you could mount some other image sensors onto your Raspberry Pi? Some of them are quite bigger than HQ sensor, and some of them maybe not that bigger, but with some really cool features. In this episode you will see IMX585 sensor made by Sony. I say made by Sony, but that just means that sensor was made by Sony. Boards are made by few enthusiasts like Will Whang and Soho Enterprises. I am in no way affiliated with any of them. I bought this sensor with my own money. And to be honest, this is not going to be a review. These sensors are not easy to get and not exactly cheap either. So, if you are that special boy or a girl, you know you already want it. I got this small one since I have some exotic lenses that don't have big image circle, so I wanted to build something to see them shine. Also, how cool is to have open source camera that records raw video files. This specific video will center around few things only. How to get capture with default tools on a plain install of Raspbian OS, what tools did I write to help me with this task, and of course, that sweet HDR mode. I know some people really wanted to see it. Now you can decide if few extra stops of dynamic range are worth the trade-offs. Oh boy, there is a lot of trade-offs and inconveniences. Also, this specific video is not about CinePi, Cinemate, or any other software that uses CinePi RAW for recording. As far as I know, all of them should work in regular 12-bit mode, so if you are looking for more of a turnkey solution, that will be a lot better. Still, they do not work well in clear HDR mode. Nothing does. There will be a lot of strange problems if trying to use any auto mode functions there. Also, preview will have really broken image, but that is a problem for everything, as you will see later. Why do we have so much problems? Most of our issues come from some strange decision made by Sony when designing protocol to transfer sensor data. You see, this camera sends 16-bit big endian value where first byte and the second byte are swapped. Raspberry Pi's ISP does not support that format, and since this is implemented in hardware, it will not be supported at all in Raspberry Pi 5. Maybe you're looking this video in the future when Pi 6 is out and it supports the option to swap the upper byte, making everything work out of the box. But as of now, that is simply not possible. If we take a look at what the ISP does, it will become clear why neither preview or any of the auto algorithms are working when you switch to clear HDR. Image Signal Processor, or ISP in short, acts like a feedback loop when trying to determine exposure or white balance of the image by basically debayering the image into usable state, running the algorithm to determine optimal parameters and then applying those parameters back to the sensor controls. All of this works perfectly when your image is in supposed format and can be decoded. When you try to do this with an image where each byte is half forward, half backward, you can only expect random incorrect results. All these operations happen in hardware, so we can't exactly go in and patch every other byte. It's either supported by ISP or not. This brings me to another strange quirk of camera software on Raspberry Pi, since all of it uses lip camera. Color correction matrices are always calculated from white balance. This is not ideal. It works if your auto white balance algorithm works, but you will have problems when it doesn't. And yeah, it doesn't work in HDR mode. I've seen that Cinemate tries to fight this by setting color calibration to a single value in sensor profile, which does work, however it feels a bit unnecessary. The way that most photo cameras deal with this is that you need to encode two color matrices, one devised from tungsten and another from D65 light for best results. These can be basically a constant for one type of sensor, and only thing that changes are red and blue gain values, which you could acquire through ISP. I did some rough calibration, and I really mean rough, and came to these values. TNG files look nice now, regardless if they are HDR or just 12-bit. Let me know if you would like to see more on calculating color calibration, as that is one quite complex topic and can probably be a video on its own. Whole process of calibrating camera to work with Pi's pipeline seems a bit unphotographic to me. On other hand, I think most of their customers are using cameras for some machine purposes, so this way is probably easier to get usable color image. Unfortunately for us, most of these fall apart when data format is not supported. Another thing is kind of interesting. As you probably noticed, there is a lot of parameters regarding HDR settings. even more so if you go to 12-bit HDR, which I won't be doing in this video. Ideally, pipeline would auto-set itself to maximize your dynamic range, but that logic does not exist at all in ISP. Now we can do workarounds for most of the stuff, but our biggest problem is the unusable preview. Makes it really hard to pull focus or do anything on the fly while the camera is recording.
But Beard,
I hear you ask.
why do you care so much about clear HDR? Raspberry Pi camera can generate HDR from 2 exposures.
Well, Sony explains this very well in their promo materials. IMX585 has the ability to read one exposure twice, with 2 different gains. That is pretty amazing. Means that you won't have any motion artifacts compared to HDR using Raspberry Pi camera. Even better, you can combine both exposures in sensor itself, so you get finished image immediately. You will get some increase in dynamic range when using sensor in this mode. There are some downsides that they usually don't mention, like increased readout time, so let me show you. Wait. It works better now. I guess you have seen metronome before. That line should be straight. I still find this to be better than motion artifacts from 2 exposures though. Also, you don't have to use it. I mean, native range is 12-bit and let me assure you, this sensor is pretty good even without HDR. People don't talk much about that, probably because something you don't have will always seem better. However, keep in mind that it is really nice in its native mode, especially for that size. So, sensor is good as it is, and yet here we are, you clicked on this video wanting to see that HDR, drawbacks or not. And oh boy, do we have some drawbacks on Pi, but I will get back to that in a second. Connecting this sensor is fairly straightforward. Attach ribbon cable, 5V power, and you are ready to go. New version doesn't even require separate power. Everything goes from a ribbon cable. Just be careful how you orient cables when plugging them in. You have infrared filter included into the C-mount, which can be enabled and disabled by software command. There is no need for external infrared blocking filter. Once electrical connections are done, you just need good lens. Do yourself a favor and skip those industrial machine vision lenses. While they give acceptable image, this is not what you got into the raw recording cameras. Get a good lens. Even photo lenses are miles above. Only real problem with small sensors is the lens selection when you want to go wide angle. Widest usable lens that I have is this Tokina 2024, made for APS-C cameras, which works out to be about 40 to 80 mm in full frame equivalent. But this is not the only lens that I will use, so take a look at the lower left corner for more technical information. Once you have hardware connected, we have to set up software. I will try to speedrun this part as much as possible, since it will change as the time goes by. We will do this on a fresh install of Raspbian, so let's go and install that on an empty SD card. Once Pi boots up, let's run update to bring everything up to date. This will take some time, but once it is finished, reboot the Pi. By the way, when you forget to type sudo, you can just use $! to reference last command. Next, we should partition and format the SSD and also make sure it auto-mounts. Run fdisk to see if the drive is there and which device name it has. It should start with dev/nvme, as you can see here. Run fdisk again, but now on this device to create new partition table and one primary partition containing entire SSD. Once that is done, you can format the drive. We want something with minimal overhead, so I picked X4 without journaling. It is not even needed in our specific case. Quick detour to install few programs to make our lives easier. I prefer moving through directories using Midnight Commander, so let's get it now. Okay, so we need to know ID of our new partition. Command block ID is used to give us that info. You need part UUID, so copy that info and start Midnight Commander. Get to etc fstab file, press F4 to get into built-in editor, and get to the end of the file, create new line, paste your part UUID, and type out the rest as in the video. This will auto-mount your SSD on mount directory. Let's test how successful we were and restart the Pi. We now need to install patched versions of libcamera programs, and Will's kernel driver. There is a guide on Will's GitHub, so we will follow it. There are no extra steps yet, so just follow his instructions. I always try to speed up things by using SSD in mount folder, hoping that it will be faster than SD card. Last step is editing config.txt file in boot folder, so that system will load proper overlay file for our sensor. Save and reboot. You can now test to see if camera is working or not. First, we can check kernel messages to see what's going on. So far, these are a good sign. This command should list some resolutions, but no 16-bit mode yet. In order for 16-bit mode to appear here, we need to switch the sensor into that mode. However, if you do it at this point, you can't record anything yet. Let's go to real hardware to see the thing working. Run this command to see the preview. This will be in a regular, non-HDR mode. You can go back to command window by pressing Alt-Tab and then Ctrl-C to stop the program. Let's switch to HDR mode with this command and rerun the preview. As you can see, preview doesn't really work. Just look at the color chart. You can set driver back to SDR mode and take a look how it should be. Now comes slightly tricky part. We have to patch Linux kernel. You see, only minutes after installing it, and you need to recompile the kernel. I told you it's gonna be fun. Raspberry Pi Foundation has a really good guide for compiling kernel, and that's exactly what we will follow with one extra step at the beginning to edit some files. As a general advice, I like to additionally edit .config file to change version string so we can easily see which kernel is running. There are 5 lines that need to be commented out or deleted in order for 16-bit mode to work properly. You can see the location of that file on the screen or in GitHub guide. You are looking for CSI_DT line for 16-bit config. After that is done, you need to start the compilation, which usually lasts around under an hour. If you are doing this through SSH, it is smart to use screen, so compile will continue even if you disconnect. After a while, that will be done, and you can compile modules and copy over new kernel. You can check kernel documentation from Raspberry Pi, as they go into way more details than I'm going to do in this video. When everything is done, reboot the Pi. Upon new start, you can see our new kernel line at the top of the screen. That means that we are running compiled kernel. Let's see if we can still use the camera. Oh, this is a common mistake. We forgot to recompile Will's kernel driver for new kernel, so let's fix that. One quick reboot after, system can see the camera again. Next, we need to patch libcamera to make sure there is one extra line telling the library to support 16-bit mode. Otherwise it will just ignore our request to record in that mode and default to 12-bit. Recompile libcamera and its programs, and then reboot for a good measure. You should be done with software setup at this point. Use this command to switch the sensor into HDR mode, and now try to list resolutions. Finally, here it is. We are now able to record the 16-bit HDR coming from the sensor in the most inconvenient fashion by typing these long command lines. On top of it, your preview is totally broken whenever you are in HDR mode, since ISP has no idea what to do with the incoming image format. Since this is not the most practical way to use the sensor, I wrote small utility in Python to help us see the image and set command line options. It was meant to run on a big PC and connect over SSH. You can try running it on Pi, it should work, but that's the experience that I don't recommend. Detailed instructions on setting up the connection to Raspberry Pi are in README file of the project and could potentially be more up to date than this part of the video. Once you clone directory from GitHub, install dependencies and run the program. On the first run you will probably get windows in random positions and sizes. Move them a little bit and hit Take Picture button. Look at the progress in log window and in a second you will see what your sensor sees. From here on, you can set a lot of manual parameters, and once you are satisfied, either record the video from here or push the script to the Pi so you can execute it there. Either way, video ends up on local SSD on your Pi. To get usable HDR, there is one nice trick. You can take a still in 12-bit mode and then use auto values to read and set parameters for HDR mode. We can get auto exposure and white balance by clicking on Read Metadata button. Now let's switch to 16-bit and take another photo. Oh, it looks like we forgot to add some gain to the second reading of the sensor. This is how we build HDR. You take one reading at base gain and then second one with high gain. You will not have any motion artifacts, since you are reading one same exposure twice. Pretty neat trick, even though it does increase readout speed. Look at the histogram to see how two readings are merged together. Two vertical lines represent high gain and low gain parameters. You can see how high gain reading makes up most of the image, while low gain helps us to not lose the darkest area of the image. Depending on blending parameter, sensor will use one reading more than another, or you can skip blending altogether if you set both values to be the same. Try to play around with options and see how sensor behaves. Video files are always saved to Pi SSD, so you can transfer them to your big PC and try to figure out what are we going to do next with them. This is just raw image data plus one text file containing metadata. It won't be readable by most software, so we have to do some more coding. However, what if you don't want to code, but just use some software? Let me introduce you to one very handy program, Fiji. Name stands for Fiji is just IMX585. IMX585 being very popular scientific image processing toolkit. Fiji comes as a graphical application that can help us take a look at the files with no coding needed at all. We basically need to plug few numbers in the right dialog and off we go. First you need to go to File, Import, Raw, and then put these numbers in settings to get the image to open correctly. This is raw image with Bayer matrix not yet decoded. Obviously next step will be to decode Bayer matrix so we can see some color. Go to Plugins, Raw Processing, dBayer 2, and make sure that the order of first row is set to RG, as this is the matrix format that IMX585 uses. We got our color now, but these are just raw readings, not really balanced, so let's fix that. Use the Select tool to select a patch of gray or neutral color, and go to Plugins, Color, IGP White Balance. You can turn option to show correction factor if you want to use it in Python code later. There you go, final image. Another interesting possibility is that if you own a color chart, you can use it to calculate much more accurate color transformation. However, you have to take a shot of color chart on your scene first. Let's import one and then go to Plugins, Color, IGP Color Calibrator. Select type of color chart that you have. You can always check if this is your chart by hitting Render button. Now you can go use Polygon Selection tool on your image to make a tight selection around color chart. Be aware that direction and order of poly tool matters. You can see that I am starting in the top left corner, which contains first chip in my color chart. Corner order has to be the same as an image produced by Render button, like you can see on the screen. See that pink squares land inside color patches. After all that, you can click on Suggest options and see what is the optimum transformation to convert colors. Select what you think is best, hit Calibrate, and from here on you can apply calibration not only to this image, but the whole directory of other images. I won't spend more time on this, as IMX585 is such a complex program that we would be here all day if I went there. Also, it is not the greatest if you want to process a lot of images for video. That brings us to inevitable coding, but I promise you, I try to keep things light. In fact, most of the code is already done and available in my GitHub. You can just get it and alter a few things where you want to change the image. So far, there are two ways to deal with raw files. First one is to do a complete conversion in our code and push this to FFmpeg to compress it into lossless ProRes file. That will be significantly smaller than whole directory of DNG files, but you are losing important aspect of raw files. It also takes forever to convert footage, as you have to debar and apply color correction to each frame. Second option is to split that huge file into series of DNG files for each frame and apply some magic sauce to EXIF metadata of DNG, so Resolve will render them nicely. ProRes Converter demonstrates how to push a frame to FFmpeg without storing it on disk, and how to process these frames in parallel, so it will be faster. Processing itself is not that great, I just used OpenCV. There should be libraries which can do the bare process somewhat better, but this keeps the code simple and you can try to write something more complex on top of this, if you want to. DNG Converter will try to include color correction matrix for tungsten and D50 light. I have to warn you up front, these are not optimal. My tungsten light was a bit sketchy and D50 was done using some weak winter sun, since that's all I got now. If you want, I could do an entire episode about setting color parameters, because this is way more complex topic than it looks at first sight. As soon as I get better measures, I will update values in GitHub. All in all, you have two programs to play around and maybe try and change to fit your needs. Perhaps you found this video interesting. Even if you don't have the sensor, this is a good look at what goes into making one sensor usable. Truly not an easy task, especially if you want it to be open source. Many people tend to ask, why didn't you use that SBC or this sensor? But the trick is, most of them come with some kind of non-disclosure agreement that prevents you from using them in open source projects. Or maybe they lack documentation, or most often, both of these things. So we are stuck with what we have at the moment. Our best bet is to hope that next Raspberry Pi will have better ISP and maybe more MIPI lanes. If you want to see something moving, try to support developers who make these things. And I don't mean me. I'm just a lunatic with a sensor who's screwing around. I mean people who are making sensors and also trying to keep CinePi alive, because in the end that is what you will use to make your camera. This is just custom to my workflow, since I don't need another camera that will be used in the field. I needed something for use in the studio, and this is why all shots so far have been from inside the house. I hope you found something useful in this video. Until next time.